Hello again. So when we move into the concept of forces and so forth, we want to remember that the force is a vector. And so I wanted to kind of review a little bit about how we add forces and how we can take their components in certain unique situations. So this video isn't very long, but the idea behind it is to give you this background before we get into some more specific details. So if we look at the idea of net forces, you can take a situation where we just have our standard x and y axis, and we've achieved these components for these 5 forces here. They may have been given to you as a navigational force or whatever, and of course you resolve them into the proper xy components, as I've shown a number of times in my previous videos. The net force in this particular case is not defined as the difference in force, is not the final minus the initial force, but instead the vector sum. This is not the average. You simply add up all these forces. So you can see, for example, force 4 and force 1 are roughly opposing each other. And if you were to pull on a string like that, there wouldn't be too much left over. So there's no subtraction, there's addition. But of course, with the directions properly encoded into our coordinates. So when we sum these forces, of course this is a vectorial sum, so we have to do it in the x's and in the y's. So in this particular case I add up all the x's, 8, 2, -2, -10, and -1, and I get -3. It's a simple arithmetic addition. Exactly the same thing for the y's, and I get a +6. So my net force in this situation is simply -3, 6, and of course when you have it stated like this, then you can also put the unit with it if you wish, which in this example is newtons. So let's draw it in now for fun. So we say, well, we're -3 plus 6, so we're sitting somewhere in this region here, roughly speaking. -3, +6. And that is what we call our resultant, or net force. And remember, if this is acting on a mass, then, and there's no friction, then this is the force that's going to be generating the acceleration. Okay, the acceleration we see in F equals ma is a result of this force. The rest of the forces are all canceled in one way or another to get to this force. This force will act on the mass and produce the observed acceleration. So we want to be very careful about that we don't have this acceleration, and so forth. You could maybe say that's mathematically valid, and maybe it is, but it's not the principle of how this is done. And we have to go forward. Remember that none of this gets any easier than this. It only gets more difficult. And so we want to start off by doing things in the correct way, so we're not having to relearn things later on. And remember also that a great amount of this you may end up having to encode in software. And this is another reason why I'm pushing you to use the coordinate system for calculation purposes, because adding up these using the cosine law would keep you busy for quite a while. Adding them up using the component system is trivial. So let's just do it the right way from the beginning. Okay, remember cosine and sine law were brought in years ago when we didn't have calculation engines, we didn't have computers, and these were different ways to try and find ways to do these calculations manually. But that's no longer the case. And like I said before, you may well be incorporating things after learning the concept and putting them into a computer program where this type of thing is very well suited. So this is a little bit of a memory aid that I came up with a few years ago. When there's 25 or 30 things to remember, usually you can figure them out. But sometimes when there's 2, we can switch things and make mistakes that we really shouldn't be making. So when the force of the mass along this ramp as a function of gravity, okay, to take this example, and this of course is applicable in many other instances, and I'll bring it up again. So this is my first time I'm introducing it to you. So the point here is it sine or cos? And now why I can't remember this stupid thing, and so you want a way that you can quickly check to see which one it is, without having to pull out your calculator, without having to worry about it, and to know for sure you're right. Remember, folks, that we all make mistakes when we're doing our calculations and so forth. These things happen to everyone. The issue is the people who know what they're doing can catch those mistakes. They can look at it for a second and say, no, that isn't right, and readjust. So let's have a look at our situation here. So we have a mass on a slope, and it's going to slide down. And I think that we intrinsically know that as we bring the angle near zero, it's going to slide less, and if we bring it vertical or close to it, it's going to slide much more so. So here's what I choose to do. If we take the extreme case in this situation, the two extremes, usually without calculation you can infer what's going to happen. So let's suppose, for example, here theta is basically 0. So our ramp is no ramp at all, it's a tabletop. We don't expect this mass to slide back and forth on the table, at least by gravity. You would have to push it, but gravity's acting straight down, and therefore there's no component horizontally. And so we expect the force along this ramp to be basically 0. Okay? And so whatever calculation you come up with, you better make sure that's true. Okay? Because we know that's right. On the converse of the case, if a ramp was near vertical, the object would basically be in free fall. Okay? And if it's in free fall, then the force acting upon it is gravity. And so once again, if our theta is near 90, we would expect our force along the ramp to be basically the force of gravity. Now, so this example, we're saying, okay, we need a trigonometric function that is a maximum here at 90 degrees and a minimum, or 0 effectively, at 0. Now this maximum is not infinity, okay, so tangent's out on this one, because here's the other situation, is that the most force that you could pull the mass down the ramp is the force of gravity. So what we want is a multiplier here, that when it's at a maximum it's going to equal 1. So we can put that in, because that's going to help us too, okay? So we have max equals 1. Now let's look at our functions. We have sine, we have cos, we have tan, okay, and if you really want to get serious, we have cosecant, we have secant, and we have cot. Okay, and we'll say, okay, theta here is 0, and then theta is 90. So this is our theta table, okay? So if our sine is 0, we get 0. At 90, I'm going to move my 90 over, it's going to get off the page here a bit. Here's my 1. Cos is the opposite. Tangent is 0, and here it's infinity. Okay? Now the cosecant is a reciprocal of these values. So therefore this is going to be infinity, okay, and this will be 1. This is, the secant is 1 and then infinity, okay? And the cotangent is going to be infinity and 0. So given what is required here, in that our function must, the multiplier that we're looking for has to be 0 when it's 0. So that allows us, we have this one and this one only left. And then it has to be 1 because we want to multiply it by the force of gravity. Okay, because the force of gravity is the maximum. We can't have any more than that. And so then that makes only this one. And therefore we have the sine function is our guy or girl. Okay, everything else is off the list. And so this is a way for you to understand a way, and you'll get very quick at this. You can do this in fractions of a second almost. You know 0 is going to be 0, this is going to be a maximum, okay, that's got to be sine, boom, move on. In the same way that we looked at a minute ago, and I won't draw as much on this one, but if we look at the one which is pushing these two things together, if we look at the normal force, which is pushing the mass against the surface, now it's the opposite. The normal force, when it's 0, okay, the normal force is effectively gravity. If you think about it, a book sitting on a table, the entire force pushing the two surfaces together is the force of gravity. Whereas if the ramp is basically vertical, then there's almost no contact So in that case here, you want Fn equals 0. So let's go back over to this one. We'll use the blue color this time. So here we have a maximum here, okay, and we have a maximum. We can use the sine function as well, all right? But when we get over here, we want a 0 at 9. Oops, I'm sorry, that's not going to work. I said a 1. I meant this one here. We can use the secant if we want to, all right? But when we get up to 90, we want a 0. And that's going to work, but it's not going to work here. And so once again, we figure out very quickly what the right ratios are going to be, as I showed in the previous video. So this law of extremes is not just for ramps. It's used in a host of cases where you can look at a situation and estimate ahead of time what would be going on when it's at one extreme or the other, and then make sure whatever you come up with as an expression is going to fit into that. And that, of course, is one of the ways that you can work through some of these things and know that you're doing it correctly. So one of the problems that we will discuss in physics, and this is just the beginning of it, is the one of an inclined plane. You have a mass sliding on a surface going down some type of a ramp. So the gravity force is acting straight down, as it always does. But we also know that we will be pushing, we'll be pulling down this way. We'll call this the force due to the ramp, or on the ramp, or whatever. And one of the challenges, as I like to suggest, is how do we approach a question like this? Now, oftentimes in textbooks and so forth, this is approached as a 2D question, and it isn't, because the motion of this, the motion of M is 1D. It can go up or down the ramp. Nothing else. So when we sort this out, I think we should be looking at more straightforward ways to compute what might be going on. Okay? So in this case, we look for a couple of things. We're going to be looking at a force that is pressing the we're going to call this the normal force. We're going to meet it again soon enough, and the force on the ramp. These are the forces that matter. So F sub n is the normal force. And F sub r, we'll just say force along ramp. And regardless of what the situation is, these will always be the forces present. The angle can be greater or less, it makes no difference. And all of this, at least to the first example here, is caused by the force of gravity. So the question then is, well, how do we, knowing the force of gravity, compute these two vectors, these two forces? They're going to be the same every time. And so what we're going to say is, and I will do another panel to illustrate this again, what we're going to say here is that, okay, we know by taking components of a force, it's going to be cos or sine. We don't use tangent, cotangent, cosecant, and so forth. These are cos or sine situations. And so what we want to look at here is, let's suppose if we were to bring the angle down near 0, the force along the ramp is going to be practically nothing. Okay? If we have a flat table, gravity does not push things along the table, it only pushes them down. So the force along the ramp then is going to be something like this. F sub r is equal to the force of gravity. Now we have to say, okay, which trig function, cos or sine, is 0 when theta is near 0? Well, that's going to be sine. Okay? Conversely, how these two surfaces are pushed together, that's the normal force. The mass surface, which is going to be a great interest to us later on, is going to be the opposite. Okay, so F sub n is going to be equal to F sub g. In this case, this is a maximum when the theta is 0, and so this will be cosine theta. Now, as we go forward in our studies, when we're doing ramp questions, this is always true. Okay, we don't have to reinvent it. We don't have to draw fancy diagrams all the time. We don't have to get lost in the computations. This is always going to be true. Okay, and we always know what gravity's doing, and we can work from there. So this is just an initial thing until we get involved with friction and other things to make this a bit more interesting. But I want to show you one other concept, but I have to rub out the board. So another case where this is typically used when students are first looking at forces and trying to learn how to add them up and so on is, this is sometimes used as a bit of a trick question, but I think if I show you this, you'll begin to understand how it works. So we have two identical masses and a string that goes over some pulleys and down the other side. And the question will be asked is, what is the tension or the force in the string? And what you'll get is a host of answers. You get choices. They often ask you what the tension is up here. Okay? So people will say, well, this one's pulling this way, this one's pulling this way. So you have two choices. You can say T1 plus T3 equals, so the tension here is twice as much as these two. That's one answer. The other one is that these two cancel out and the tension here is 0. Now, this is where we get too involved with mathematics and not thinking about what's really happening. And that's our critical obligation in a physical science course. We cannot just use the math. So let's look at the basic consequences first of what would be happening. And you need to do this when you study these kinds of questions. If the tension here is twice as much, okay, then that's going to pull these masses up. And this string will shorten, which would be a pretty amazing thing to watch. So that's not going to be happening. If the tension here was 0, as some suggest, then this line would be limp. And that would also be pretty surprising. So we can see by just our quick draw answer on these things is that we can fool ourselves. But I can draw a picture for you that will set it another way. Okay, so let's try this for a minute here. We're going to rub this example out a little bit. We'll get rid of this fellow. And what we're going to do instead is we're going to construct a wall here. A barricade supported, okay? We're going to put a ring in the wall. So this is just an obstacle that's nailed down to the table, okay? So to the table. Okay, now if I was to ask you what the tension in the string would be, this thing's holding it solidly, you're going to say, well, okay, then the tension here is the same. It's tension 3. It's just, all it's doing is going around the corner, right? It's a very easy question. And all I did was put an obstacle here, and it makes perfect sense. So the question then is, what is this obstacle doing? Okay, what is this obstacle doing that keeps this mass from moving? So this is pulling on the obstacle by a force of mg here, and this one here is pulling, okay, on the other direction to offset that, so that we have no net force. Okay, I didn't say there's no forces. I said there's no net force. So that's a good point here. Let's just do that. We have here, we have the force, we have the tension 3 plus the force of the wall, okay, will equal 0. And we know it's 0. Let's say that we have, so the net force equals 0 because the acceleration equals 0. So you know that. That's not something that is how'd you know that? This thing is not moving. Its acceleration is 0, therefore this must be 0. So whatever this force is, it must be offset by this. So that's what's really important. And we see that this rigid object, okay, is fast here, and that's supporting this mass. And we pretty much get that. Okay, now we're going to return to the initial question we had in front of us. Let's repair the damage here. And we'll put a ring here. And now we're going to put our mass back. Okay. And we're going to put our... So, and we also know from this one that T3 is equal to negative force on the wall. And in this case here, this is, we're going to call this T1, okay? So T1 is equal to negative T3 as well, because this one's pulling this way, this one's pulling this way, this one's pulling this way, and that one's pulling that way, right? So what's happening here is the net force is 0, in that there's no acceleration. But from the ring forward, we have a force acting this way. From the ring this way, we have a force acting this way. Now, of course, we can make the ring vanishingly small. And so when you're finished with a question like this, is you show that tension 1 is equal to tension 2 is equal to tension 3. And you can see by putting that wall in there that really the problem is very straightforward, but it looks tricky. And you will often fool yourself when you first look at questions like this. But it is the truth of the situation. This is exactly the same thing as a tug of war. You have Team A pulling here, and Team B pulling here, and initially there's no movement. Okay, the ring or the flag or whatever you want to call it doesn't move. There's no acceleration. The net force is 0, but each side is pulling for all they're worth. All right? And that's really important to remember, is the distinction between the forces within the situation, as I showed you in my first diagram, and what is the net force in a given situation. And net forces are very important. All our buildings have profound amount of masses and structures in them, and tremendous amount of forces in them. But we all pray that the acceleration of our building remains 0, because the forces, one way or the other, sum to 0. Hopefully that's put you on the right footing, and you get a chance to remember how we add force vectors and how we can take components on a ramp and the Maya law of extremes, which can really help you when you're not sure what to do in some of these situations.